Hello everyone, this is Xiaochun Liu from University of Wisconsin-Madison. In this work, we demonstrate a fast diffraction imaging algorithm for a hidden scene reconstruction.
We shoot a pulse laser from the hardware. Notice that this pulse laser have 70 picosecond temporal resolution, which is equivalent to a 2 cm light pulse traveling in air. This short laser pulse traveling through the scene and hit the wall, which is in the line of sight area. Next, we have another focus detector on the wall, which can collect those reflected light. Currently, the most popular one we use to detecting those reflected light is called single photon avalanche diode. Finally, we acquire some signals at different focus detector points and process them through computational algorithms.
So how does those captured signal look like? There are two commonly used acquisition schemes. One of them is called non-confocal acquisition. This means that you collect measurement from a set of detector points by shooting a single laser on the wall. On the other hand, if one co-located a pulse laser and the detector point and scanned them within the detection area, this acquisition refers to confocal acquisition. Notice that most past computational algorithms are designed for the confocal acquisition, whereas there are only a few work focusing on the non-confocal one. Especially given the array detector, non-confocal acquisition will have scanning-free advantage. However, the inverse methods associated with this type of acquisition has a huge computational complexity barrier. Thus, in this work, we focus on the non-confocal fast recovery algorithm design. Here are the captured signal reorganized in space X and Y and T format, which is just like a spatial temporal cube. This is how the non-confocal data look like. The main framework we use is called Phasor field non-loci imaging. For each captured signal in time, if one applies a one-dimensional Fourier transform, then we have shown those captured signals in frequency are equivalent to the wavefront that exists at the aperture of regular optical imaging system. So now, one can understand that signals that are captured on the wall are some diffraction patterns. Then, to reconstruct a hidden scene, we have to propagate this wavefront back to form a hidden image. So, what kind of diffraction propagator that are suitable for this diffraction process? Let's now have a closer look on the diffraction propagation model. Given the input and output field on a plane in Cartesian coordinate, we can describe the output y as the convolution between input field x with some convolution kernel h. In the Phasor field non-loci imaging method, this h will look like this. In fact, this diffraction is called Rayleigh Sommerfeld diffraction. Remember that we collect multiple frequency wave components on the wall, and this Rayleigh Sommerfeld diffraction applies to all wave components. Let's apply this Rayleigh Sommerfeld diffraction to a single frequency wave component. This will look like a digital refocusing around the corner. The main formula to process those captured multiple wave components is as following. Px, y, omega refer to the captured wave component. X and y refer to the spatial dimension, and omega refer to the frequency dimension. We also have the convolution kernel h that is calculated from the Rayleigh Sommerfeld diffraction. Then, if people evaluate this integral for non-negative time sequences, you can form a movie around the corner. These just look like you are actually seeing the illumination pulse traveling through the hidden scene. It can be used to review a high-order scattering event around the corner. If you set the time t equal to the time when the pulse arrives, you can substitute the time t variable to form a stationary 3D image. In our work, we also demonstrate a spatial section-based processing method. This allows people to reconstruct hidden images based on the desired field of view in the reconstruction. We upload all code and data to our webpage. Feel free to send us questions. Thank you.